Audience? Audience? Okay, this is my presentational aid speed I did on calculus. So, algebra, just downright boring, right? Geometry, I guess it's kind of cool to figure out shapes and sizes of stuff. Pre-calculus, when am I ever going to need to know the side of a triangle, how long a triangle is? And then there's calculus, the real math. The stuff you've been learning all this other stuff for. The stuff where in terms of predicting the real world that really counts. Sure, the mere mention of the word calculus can incite fear and pain into a person's brain, but I'm going to try to show you how calculus is nothing more than just a complicated version of slopes and interpreting these slopes and graphs. Anyways, so in ancient times there was little tits and bits of calculus, but it wasn't until this man, Sir Isaac Newton, came around that we really began to see uses and interpretations of the real world calculus. As you may know, Newton came up with controversial ideas about the shape and size of the world, and he used calculus to figure this out. So the story goes that he discovered gravity while sitting under a tree after an apple struck him on the head. And my question to you is, how fast was this apple going when it hit his head? Or more precisely, how fast was this apple going 1 second after it left the tree? For this, we need a sub-discipline of calculus called differential calculus, which deals with the rates at which quantities change. For example, miles per hour is a rate. We're measuring how many miles you're covering per hour. So, like I said, calculus is just a complicated version of slopes. And like I said, in differential calculus, we're measuring rates. And the best way to interpret this is through a graph with a line. And I'm sure many of you learned the whole rise over run deal, which the slope of this line is describing how fast this value y is changing along this value x. So if we have a slope of 2, it means for every 1 that you move over on the x, you change 2 in the y. And this is basically differential calculus in a little bit more complicated way. You can see it's easy to calculate the slope on a line, but when we get to something like this, it can get to be a bit more difficult. So how do we go about calculating these slopes on, say, a graph like this? Well, for this, we need Newton's difference quotient, which may look a little bit difficult right now, but after I describe a couple of these symbols, it may seem to be a bit easier. Now this symbol on the left, this is the derivative, or the slope I was talking about. This is the value of the slope right here. So if we go to this picture, right here, the slope of this line is f prime x. And then this top jumble right here is the difference in y as we move a symbolic value h on this graph. So let's go back here. We start here, at this point, and compare it to a point over here, moving a distance h. And this is going to have a value, and this is going to have a value based on the data of this line. And we divide it by h to get a value. And the basic idea of differential calculus is, as this h gets smaller and smaller and smaller, we get a better interpretation to the slope of the line that describes the rate of change at this point. So let's go back to that apple problem. We wanted to know how fast this apple was going 1 second after it dropped. So let's say we had means by which to keep track of the apple's distance at every second along its fall. We would end up with a graph like this, a parabolic graph that describes the apple's flight at different points in time. And we can see that due to gravity, it's accelerating. So the farther we go along the time, the more and more distance it's covering. You see right here, it's covering slow ground, and then it starts to pick up more speed along here. So we wanted to know how fast is this apple going at 1 second. Well, let's start with an h of 0.5. So we locate this point, f of 1, at 1 second, and we can see it's fallen about 4.9 feet. And we want to use a step size of 0.5, and we can see up here, from my Excel graph, it's fallen about 11.03 feet. So from here we plugged in the value of f of 1.5, f of 1, and then the step size of h, which is this distance here, and we obtain a value of 12.27, which is only a rough approximation, as I will begin to show you right now. So let's take a smaller h, and this is about 0.25. And from my data, I have f of 1.25 minus f of 1, which at f of 1.2 seconds, this apple has fallen 7.5 feet. And we know how far it's fallen at 1 second. Divide it by the step size, we get a smaller number, 10.9. So let's cut the h in half again. You can see different points, 6.153 after 1.1.25 seconds. Get an even smaller value, 10.4, and we could see as we shrink the h a little bit more, get smaller again, but you should notice that the smaller we go, the smaller this value is changing. First it went from 12.3 to 10.9, then it's 10.4, 10.1, and it's smaller and smaller each time. So we can see that as h is shrinking, we're approaching a certain number. In our case, this number is going to be 9.81. So this is the speed of the apple after 1 second. So I hope that was a little more clear explanation of calculus, and that now you can begin to understand that calculus isn't anything but just a more complicated version of slopes, and it's just the means of interpreting these slopes where we get to the meat of calculus. All right.